The results of the delayed choice quantum eraser experiments can be mind-boggling in many ways, yet many people misunderstand the implications because they don't understand the experiments. So I'd like to explain the most famous one from 1999 and share the shocking implications of the experiment. But first, we need to understand what a delayed choice quantum eraser experiment means to do, by modifying the original double-slit experiment. So if you don't know what the double-slit experiment is, I recommend stopping here and watching this video on it. Now if you already understand the original double-slit experiment, then you know the implications of placing a measuring device at one slit. Without the measuring device, when we shoot photons through a double slit, we can't then know which slit they went through or which path they took. So in other words, we cannot know the which path information. Now for reasons we'll discuss later, because we can't know which slit it went through, the photon acts as a wave and goes through both slits, interfering with itself and creating an interference pattern. But when we add the measuring device at the slit, we can know which slit it goes through. However, because of this, a different pattern emerges. Instead, we get what is called a clump pattern, meaning we know the which path information, because we looked to see which slit it went through. The very act of obtaining knowledge of which slit it goes through means it only goes through one slit, and changes the result and how the electron acts. Now delayed choice quantum eraser experiments are pretty much the same type of experiment, except for one big exception. They look to see if our observation is really what is causing the particle to collapse. Perhaps there is something else doing it, and we can trick the system into showing us it. So instead of placing a detector at the slit, two are placed past this, where the particles land. But just before the particles land here, it is pulled away and the two cameras capture the results, after they went through the double slit. If they observe a wave, then the particle went through the double slit as a wave, and just observing or knowing the path information doesn't cause them to collapse to particles. So perhaps one could argue what is causing collapse is something else, like interaction from a physical measuring device. But on the other hand, if they collapse to a state of particles at the moment of detection, then even though they went through the slit unobserved, and should produce a wave pattern, the very act of observing instantly transforms them into particles. But not only that, a back history is loaded up so that particles went through the double slit instead of a wave. Well, in 2007, this thought experiment was put to the test, and the results showed that if the film is pulled away, we observe particles. Observation instantly collapses them to particles in one definite position and loads up a back history so they went through the double slit as particles. Once we have the knowledge of the particle's position, we know the which path information, and this causes a clump pattern instead of an interference pattern. See, observation is about knowledge, a conscious observer having knowledge of the system, and this is what is argued as what causes the particle to have one definite position. The act of observing is the mechanism for collapse. This is better demonstrated from the famous delayed choice quantum eraser experiment from 1999. As you can see, this looks complex, but I'm going to break this down and attempt to simplify what is going on here so we can understand it. I'd also like to thank Ross Rhodes of bottomlayer.com, who is a great commentary on this experiment, and was nice enough to reply to my emails in helping me write this. His article about the experiment was actually reviewed by Dr. Kim, who ran the experiment, so it is a pretty trustworthy article. The experiment begins in the top left corner, with the laser firing two entangled photons either through slit A or slit B. Now it is truly random which slit it will fire through, and because we have no measuring device at either slit, we cannot know which slit the laser fires through, until they pass through and are detected on the other side. So at each firing, it will either go through A or B. Now the first prism splits the entangled photons and sends them in different directions. The top one goes to detector 0. Now if the photons only hit D0, we don't know the path information, since when the photon arrives, it could have either come from path A or path B. So because we don't know the path information, it should produce an interference pattern if it only came here. If we could place a measuring device at the slit, we would know the path information, but with just a result from D0, we don't know the path information. So because of the lack of knowledge we would have about the system, the particle would act in a way as if it goes through both, becoming the wave of possibilities it could have been, instead of one of these possibilities, if we knew the definite path information. But the other entangled photon goes the other way, and because it is entangled, it will affect the result of its twin that went to D0. Now the other photon from either A or B goes through the prism and hits either BSA or BSB. At both of these, there is a 50-50 chance it will either pass through or bounce off and go to either D4 or D3. Now if the photon hits either one of these detectors, notice what happens. We obtain which path information. because the only way the photon could hit D3 is if it came out of B, and the only way it could hit D4 is if it came out of A. There is no way a photon that came out of B could hit D4, and vice versa. So if a photon hits D3 or D4, we will know the path information it took, and we will get a clump pattern. Now if the photon randomly passes through BSA or BSB, it will either bounce off here or here, and it has a 50-50 chance of passing through BSC or bouncing off of it. So if the photon passes through BSA or BSB, we lose the path information, because if it hits D1 or D2, it could either have come from A or B. We can't ever trace the path information back to A or B. So when they hit D1 or D2, we should get an interference pattern, demonstrating the photon went through both slits, since we don't have definite path information. Now here is one of the important implications of this experiment about what is causing collapse. Some argue physical interaction from the detector is what is causing the collapse, but if that was the case, D1 and D2 should cause collapse every time. But that is not what happens. If a photon makes it to D1 or D2, they always display an interference pattern. Yet every time a photon hits D3 or D4, a clump pattern is formed. But the only difference is what we, the observers, know about these two stations. Because of the experiment setup, we know that if a photon hits D3, it will always be a clump pattern, showing the photon only went through one slit. If it hits D1, we know it will always be an interference pattern, showing that the photon acted in a way as if it went through both slits. But the only difference between these two is what we, the conscious observer, knows about the system. Our knowledge of the system causes different results in how the photon will act. If it was all random and not caused by our knowledge, we should get some clump patterns at D1 and some interference patterns at D3. But that is not what the experiment shows. We always get a clump pattern at D3 and D4 because whenever a photon hits here, we always know the path information. And we always will get an interference pattern at D1 and D2 because we can never know the actual path information. So the photon acts in a way as if it goes through both. Whereas at D3 and D4, the photon only goes through one slit because we know the path information. The particles act in a way that correlates to our knowledge. See, what causes collapse is knowledge, and knowledge requires a knower. Sir Rudolph Peirce said, "The moment at which you can throw away one possibility and keep only the other is when you finally become conscious of the fact that the experiment has given one result." You see, the quantum mechanical descriptions is in terms of knowledge, and knowledge requires somebody who knows. Now the other implication is even more mind-boggling, because the photon knew beforehand where it would end up. How do we know this? Because of how its twin acts at D0. The twin photon registers at D0 before its entangled twin ends up at a detector, and whatever registers at D0 always correlates to wherever its twin ends up. So if the twin hits D3 or D4, D0 always registers a clump pattern to correlate, and always an interference pattern if its twin lands at D1 or D2. So either the photon has a highly complex computer built into it, so it can know the future, or we have an idealistic picture of reality, and our knowledge of this system affects the past by loading up a back history to correlate with our knowledge. John Wheeler said, "It begins to look as if we ourselves, by a last-minute decision, have an influence on what a photon will do when it has already accomplished most of its doing." We have to say that we ourselves have an undeniable part in shaping what we have always called the past. The past is not really the past until it has been registered. Or put it another way, the past has no meaning or existence unless it exists as a record in the present. An experiment from 2012 took this a step further and brought back in the conscious free will of the observer. To understand this experiment, picture two entangled photons are sent from either station A or station B and separated. The first from each pair is sent to one of two different measuring devices here. Observers Alice and Bob are each stationed here, but do not look at their measuring devices yet. Both of the other entangled photons go to a third measuring device, where Victor is. How Victor chooses to measure the two particles determines what Alice and Bob see their entangled photon as. This happens even if Victor decides after Alice's and Bob's devices have measured them, but before Bob and Alice actually view the results. Therefore, a conscious choice affects behavior of previously measured but unobserved particles. Asher Perez, who developed the original thought experiment, says, "If we attempt to attribute an objective meaning to the quantum state of a single system curious paradoxes appear. Quantum effects mimic not only instantaneous actions at a distance, but also, as seen here, influence of future actions on past events, even after these events have been irrevocably recorded. John Wheeler's original thought experiment shows the implications of this. He explains by asking us to imagine a distant star that emits a photon billions of years ago and sends it towards Earth. However, on the way it must pass a dense galaxy. Gravitational lensing will make the light bend around the galaxy, so the photon can take one of two paths around the galaxy. Billions of years later, upon reaching Earth, an astronomer chooses to use a screen type of light projector that encompasses both sides of the surrounding space, without focusing on a specific region. Therefore, the photon will land somewhere along the field of focus, without anyone being able to tell which side it took. So it will display an interference pattern, demonstrating it took both. However, the astronomer could choose to measure the incoming photon with a binocular apparatus and focus on the left side of the galaxy, while the other side focuses on the right side. In this second case, how the astronomer chose to measure means the photon could have only taken one path, and would display a clump pattern. So in this thought experiment, how we choose to measure now affects how the photon acted billions of years ago. Our choice affects how the particle acted in the past. So the factor of time has nothing to do with quantum mechanics. And the interesting thing about this is, John Wheeler based this on the mathematics of quantum mechanics. Mathematically, this is what was predicted, and the exact same result is what we see when we put it to experimental test.